that we're recording. I'll stop recording when the lecture is done. And what will happen is this will be in our Teams account. So Microsoft, if you want this lecture, you have to go to, open up your Teams, and then it should be there. It should be under. You'll see something like, if you can see my screen here, it'll probably be under one of these, because this little symbol means that we have a meeting going. And if we do chatting here, then and if it's recorded and all that, then it's should have a date here, but it'll store it here. So you could always just open up your Teams account and just click on this, lecture, and you'll have the recording. So going forward, right? Because I just did that. You don't have access to this one, MAE330-11. But it says it takes a little while, but there I just recorded the lecture, and it should pop up right there. So I haven't seen it yet, but anyway, hopefully it goes there. Now you guys can. I never used to record my lectures, right? I guess now everyone's doing it because on Zoom, right? Do most of your teachers use Zoom? Guys?
Yes.
Yeah. Everyone's using Zoom. Okay. Yeah. I apologize again in advance that I am not using Zoom. I don't have anything against Zoom. I think it's cool. I just I thought it would be cool to do Teams because it's kind of like Discord. So if someone it has this little Discord-y type of stuff right here. So for example, let's you guys are looking at my screen. You should have an icon that looks like this, though there should be a little camera symbol as well. See the little camera symbol right there. If I click on it, then I have a chat, right? And this actually someone asked me for the link. So I can say, hello, everyone. And I don't know. I'll just put this one here for now. And that's, oh man, I shouldn't have put no, I'm sad. Sorry about that. No, but long live the Black Panther, because man, I'm heartbroken. But anyway, this is how you can go ahead and talk to each other via this chat, and and you can add me just like you do on Discord, and it'll send me a message, and you can say, hey, I can't do problem number 1.1-47. Can you help me, or things like that. We also have someone created a Discord page or a Discord site, but it's redundant to me. I mean, this kind of does the same thing. And then someone opened up for those of you guys there, someone opened up a video conference, and I was about to join it, but I was thinking, no, we're gonna create confusion again. Remember, I said I would create it, I would do the video, and then you guys would join me. But a group of you guys, a group of rebels went and started the video, and I think 3 or 4 of you guys joined, and I had one of my fearless students go tell you guys to switch over. So from now on, I want to do that. I want to start a meeting, but I am going to go and put on Beachboard. I think I said this time, right, I put a news item, and I put the link in there. So if you go to Beachboard, to your Beachboard page, right, I just threw that up there right now for those of you guys that couldn't. I don't know if anyone grabbed this link and went on, but if you just have your Teams account open and I start a meeting, it'll automatically tell you to join. It'll invite you. All right, so sounds good, everyone? Okay, we're going to start with the lecture.
So it's better for us just to wait until you start the meeting, not
yes.
Yeah.
Don't jump the gun. You guys have this ability to have meetings with each other at any time.
Yeah, well, the
right,
thing is, somebody starts a meeting or starts the join a meeting or something like that, and like a couple minutes ago, we had like 4 meetings or 3 meetings going on at the same time.
So what I'm going to do now to avoid confusion, I would just love for you guys not to start a meeting. Just but if you, so what I'm going to do just for confusion's purposes, I'm going to, the only thing I can do is just go to Beachboard and post the link right there. Right as I say, see it says 6:52, the class starts at 7. Remember, I'm going to try to start at 10 minutes before class, and then I'm just going to grab that link and put it in Beachboard so that there's no more confusion. I'm sorry. There is ways for me to go on the Teams here and to prevent people from having meetings or starting the meeting. I know, I'm sorry. This is very confusing, but I don't know what else to do because you guys can start a meeting. Anyone can start a meeting right now, and then you're going to jump to, you know what I mean? So that's the only way I can do it, is to basically put the link in Beachboard. Start the meeting, put the link in Beachboard. All right. So if you're okay, if you guys are, what do you call it? Like really I don't want to say worked up over this. If you want, just like, you know what, I don't want to just turn on. I don't want to just join the meeting and then there's two of us, right? Then wait for the link to appear in Beachboard and then you can click it. But I'm not going to post it way ahead in advance. I have to post it 10 minutes before class. You know, it's a good thing too. That way, there's more security that way for me. I mean, I don't know how often people mess or jump classes and do stuff, but right. So that's better for me too that way. So, again, to repeat, 10 minutes before the class, I'll start the meeting, and then I don't know if I should just put at the title up here, put MAE330-11 and put, you know, the original, or put my name here, or I don't know. So in case you guys are on Teams already and you guys can find the right meeting, but if there's any confusion, you'll have to jump over to Beachboard and grab the link, which I posted. I didn't post it in my other lecture, my 07 lecture, because I messed up. I copied something before and I kind of erased the link in my on my what do you call that? My desktop or whatever, my in my register, and I couldn't link it, so they were kind of they weren't too upset. They all figured it out, but anyway, sorry. So everyone's here because I have 38 people. Now I only have 36 people in my class, so this is awesome. Okay, and I am recording, so you are being recorded. See, we're making progress, guys. So, all right, let's go ahead and start the lecture. All right, so a little bit on homework 1. I didn't plan on. If you guys have any questions on homework 1, let's save it to the end, okay? Because during my office hours, because the homework is not really due till Thursday, right? So on Beachboard, this class, I actually forgot that I didn't put a Dropbox folder until a few hours ago. So I think around did it. So it's there, and it's a due date of Thursday by 7 p.m. So you know, and some of you guys are chatting amongst each other to ask questions. That's cool. There's I told you guys there's a student opened up a Discord, and I think it's in here somewhere. So there's people who are asking questions there to each other, and you guys are helping each other out. So this is cool. You can do that here. Again, I showed you already on Teams. You can add each other, or you can just send a general question to someone, to the whole class. Hey, can anyone help me with this problem, or, you know. Okay, so if you have any question on homework, again, it's not due till Thursday. Let's wait to the end, if you don't mind, so I can get going on chapter 2 here. All right. So chapter 2, energy analysis. I'm gonna go ahead and skip this, but the objectives here are pretty straightforward. We want to define what energy is in its different forms. We want to have a discussion about internal energy. We're going to talk about energy transfer, though we're not going to get to that until Thursday's lecture. But the majority of what I do is kind of falls into this category here, energy transfer in the forms of heat transfer. Then there's to define the concept of work. Again, most of this we're not going to get until the next lecture. I only was able to cover the first 3 or 4 bullets. And then we'll talk about control surfaces and how to do an energy analysis. And we'll talk about efficiencies. And at the end, energy conversion and what that means to the environment. You know, global warming and heating the atmosphere and all that. So we'll talk a little bit about that. All right, so but I really want to talk about this problem here. This is a fascinating problem. And I'm going to go ahead and just take a snapshot of this. Let's see there. So I can post it onto a paint board here. And then just instead of drawing it, be able to just point to it and stuff. And all right, so we have, so here's a problem, okay, that we want to solve. So the you have a refrigerator here that's operating with its door open in a well-sealed, well-insulated environment. So you have it's plugged in. So what you do is you basically number one is you plug it to the wall. What I mean by it is the refrigerator, and then you leave the room. You leave the room, but you close all the but close all doors / windows, and come back, say 2 hours later. Then the question is, will the room be number one, or I should say, yeah, I should say A, hotter, B, colder, or C, same temperature. All right. So what do you guys think? Will it be A, B, or C? Hotter, colder, or the same?
Colder.
A.
Okay.
Depends on the size of the room.
It would be
Colder,
A.
Same. Oh, A.
Conservation of energy. Yeah, it would be A.
A. Okay.
C.
So we got another C here. All right, I don't mean to take a tally, but no one's saying colder, huh? All right. Well, one person said colder. Okay. Because this was my guess. All right. When I did this problem was presented to me. Okay, when I was a grad student in 1995, actually, it was like more like 96. I was interviewing for a job. I had just pretty much finished up my degree. I was on my last semester, and I had an interview with Hewlett Packard, and HP had a big facility in Oregon. And actually, I passed on to the next interview. I finished. I was successful in the phone interview, and then I went on the on-site interview, and I didn't get the job. But this problem was asked of me, and I said, I said B, colder, right? Because doesn't that make sense? It's a refrigerator, right? You open it up. But the right answer is actually this one, is hotter. All right, and it's not the same, but it could be the same. But I had a student challenge me on this because I used to think it was the same, and maybe we'll entertain that one too. But the answer is hotter, right? So it's hotter, and let's explain why. So can anyone just tell me why it's hotter? Maybe.
Yeah, because
there's energy going into the room.
Yep. So there's energy going into the room. Yeah. So there's heat energy going into the room, coming from where?
Coming from the outlet.
Yes.
Yeah. Well, yeah, the energy is coming from the outlet, but where's the heat coming from?
It's coming from the compressor and the AC unit that's in the actual fridge. Exactly.
So there's a compressor here in the back. But even more fundamental than that, what is actually here on the fridge, for you guys that know ACs and refrigerators, what is here that expels heat?
What,
A
like
radiator.
a motor?
Exactly. Someone said like a radiator. So the motor does, the compressor is going to give off some heat, and we're going to say Q is heat. But there is actually, some of you guys are getting a little bit more, maybe because of my later classes, or you guys are a little bit smarter than everybody else, but I'm getting a lot more fundamental or good engineering answers, but there is a heat exchanger and either it's in the back of the refrigerator or it's at the bottom. Mine's at the bottom, my refrigerator, but I had an older refrigerator that's in the back. And so usually, like if I open if I'm hungry and I'm opening the fridge and I'm standing up here like this, right? This is me here, and I have my hand there and my head's here. Sorry for this really bad drawing, but I feel heat coming from the bottom of my fridge. And that's because the coils are down here expelling heat. So what happens is that for the refrigerator to do its job, which is basically dropping the pressure of the inside. So I'm going to say Q, just say Q negative. So it's absorbing heat, right? That's what a refrigerator does, is it absorbs heat. It only is functional. It only does its job if you close the door. If you don't close the door, then it doesn't really serve a purpose, right? But if you did open the door, it's still going to absorb heat, but just say, but it is also going to expel heat and a lot more of it. Why is it going to expel heat and a lot more of it? Well, because this is Q. The reason it's going to expel heat so it's going to pull heat. It's not just going to grab heat and throw it out the back. It's going to do that, but there's also someone mentioned the power loss here. There is and then there's a compressor loss. It's going to throw more heat out than it pulls in. And if it didn't, it would actually violate the second law of thermodynamics, right? It would be actually creating energy. If it absorbed more energy than it threw out, then it would be violating the laws. But anyway, let's not get all fancy with science. But it is, for those of you guys that know refrigerators, it does throw heat out the back. And because the refrigerator is not 100% efficient, then the amount of heat it's going to throw out the back is going to be, it's going to be the heat that absorbs plus the electric, all the motor losses and the electrical losses and everything, it's going to throw out the back. So it's always going to be more heat it expels. So therefore, it will heat up the room. No, not even a question. There's a better way of looking at this. So keep in mind, the room is well insulated, right? So the assumption is that the room is insulated, right? If the room wasn't insulated, then the argument would be, well, I'm going to lose some heat, right, off the top and whatnot. And so it only works because the room is well insulated, or we're going to learn this term later. It's called adiabatic. It's a Greek word that means no energy passing, but in our case, it's no heat energy. So, but there is even a better fundamental. So if you were going to be like kind of the person that make professors like ooh and ah a little bit more, to look at it even from a higher level, because from a standpoint of someone that really knows their mechanical, you guys come up with this. Again, I didn't. I thought it would get colder. Me being an idiot, right? But this was me because I didn't know too much about refrigeration. I didn't know that. I didn't realize that refrigerators had. I didn't, and not that I didn't realize. I just didn't know. It's just I was ignorant about refrigerators. But you guys are not ignorant. But there's another fundamental way of doing this. Is let's assume let's do orange here. So the way we do an energy analysis, and you'll get this later by chapter 3 for sure, is that we look at a boundary and we look at what crosses the boundary. Right, and then we do a balance, and then we look at a balance, energy balance. So in other words, we say, well, is there more energy leaving than coming in? Is it equal? And then if so, it's steady state, and therefore we can kind of calculate temperatures. But let's look at what's crossing the boundary. So what's crossing the boundary? So we have electricity that's crossing the boundary, right? The boundary is the room. So we're going to say, we're just going to say power. I don't like electricity, but power. We have power crossing the boundary, going in the form of electricity, going to the refrigerator. What else is crossing the boundary? We only really care. This is the only energy that I ever want you to worry about crossing a boundary. So is there mass, kind of like fluid flow? Because if you tell me that someone left the window open and air is coming out, then it's a different problem. Is it? This is the only thing I care about crossing the boundary. Is it mass? Is it work? You know, like electric work, but also electric, mechanical, or the other one is heat. So these are the only three things I care for crossing the boundary. Well, we know that everything it's sealed off completely, so it's not fluid. There is no fluid flow, and then it's also adiabatic, right? It's well insulated room, so there's no heat. But there is work. There is electric work, right? And it's here. So, so what goes in? Maybe let's put it on this side. What goes in? See energy in. This is chapter 3 stuff. In a steady state environment where everything kind of settles out, the energy that goes in is equal to the energy that goes out. There is no energy coming out. There's only energy. There's electric energy coming in, electric work, and on this side, there's zero. There's nothing. Nothing's coming out. So you have a situation where it can't be stable. Therefore, it cannot be. It's not stable. Or not steady state. Can't be, because there's only work coming in, there's nothing coming out. So therefore, the temperature will only increase, right? So therefore, the room's going to get hotter. So if you told me that the energy was stable, like there was the same amount of energy coming out than coming in, then I would go with the same, right? A couple of you guys mentioned the same. And that's actually better than mine. My guess was colder, right? So colder would basically not make any sense. It would violate the laws of physics. Hotter is what makes sense, because this is the way of looking at it. There's only one thing coming in, nothing else is coming out. So if energy is coming into a system and nothing's coming out, it's going to increase in temperature. That's the more like high level philosophical way of looking at it. Okay. The more grungy engineering way of looking at it is like, well, yeah, there's coils in the back and the heat's coming out more than it's what's coming in. And that's true too. Okay, there's a bunch of different ways of looking at it. But yeah, so I didn't get the job, and I don't think it was because, maybe it could have been part because I didn't get the answer right. But again, doesn't really matter, because the job that I ended up getting at instead of Hewlett-Packard was much better, and it gave me a path actually eventually to head to start working for NASA. So if I would have got hired from HP, then who knows what, I probably would have ended up in Oregon. Probably maybe protesting in Portland or something, but I wouldn't be here, I don't think. All right, let's go back to any questions on that, or can I move on? Okay, so the same thing could be said about a fan, right? So a fan, same. Now that I mentioned that, right? Now in a fan, it might be, well, you do have energy coming out for the motor. So one or two of you mentioned the compressor and the refrigerator expelling heat. The fan has a motor, and that's kind of something similar. The motor expelling heat and eventually heating up the room. I mean, if it's well sealed, there's nothing escaping, and then even the little bit of motor heat, even this coil getting a little bit hot from the resistance losses, will heat up the room eventually. Not as much as the refrigerator, because the refrigerator has like order of magnitude more power, but it's the same thing. So if you have your ceiling fans and you leave them on, that's not going to cool your house down, right? A ceiling fan only moves the air to give you the cooling feeling, but in actuality, it's heating up your house. But these are such low power that's as long as the room is somewhat large enough, you're not going to really feel it. All right, so now we're going to go into the actual lecture here. Forms of energy. All right, so the lecture start at 7, is going to end at 8. All right, so I'm going to go ahead and.
Professor, and what chapter is this lecture starting from?
This is chapter 2.
Gotcha.
Yeah, so chapter 2. So the PowerPoint slides are actually in Beachboard. If you go to there's a module that says lectures, and there's chapter 1, chapter 2. We're going in order. Next is chapters 3, then 4, then 5. We're going to go in order throughout this class. We're actually a little ahead right now. we really have till this end of this week to finish chapter 1. Sorry, but I want to go a little bit faster because we end up slowing down a lot, and so I'm kind of picking up the pace a little bit. So all right, so chapter 2. We're in forms of energy, which is slide 6. So I'm going to go ahead and start writing stuff here. All right, so the forms of energy. Then in general, forms of energy, they're going to be thermal, right? They're going to be mechanical. And what else? What are the forms of energy? Well, mechanical is inside of it has kinetic and potential. But what other forms of energy do we have? We have electric, right? Electric, and then there's other ones. There's magnetic. There's chemical, and then there's nuclear. What else? Kinetic. So there's kinetic potential, mechanical. There's different forms. I haven't covered everything here, but really the only ones that we're going to be focusing on here in this class, it's not just thermal, but it's thermomechanical. Right. Thermomechanical. Electrical is a form of mechanical work, by the way. So electrical could it come inside this bracket? I know, because like electric motors, right? So electricity will give us mechanical energy pretty easily through electric motors. Heat, when I mean by thermal, I mean usually heat, right? And heat will not give us mechanical work, but we could, like directly it won't, but we could burn something and cause it to move a piston and get some mechanical. So there's ways of doing that. We'll actually dedicate several chapters on that. All right, so that's the forms of energy. And then the total energy, right? Total energy will be everything added, right? So total energy would be all energy in a system, what we call a system. So the refrigerator in a closed room, that's a system, right? Something where you isolate. So we isolated that refrigerator from that room or from that house, right? And that's a system. So anything that you focus on your attention to is called a system. All right, so there's, what else can I tell you? Okay, there's something called internal energy. Someone in my other lecture asked me to give you an example of internal energy, but let me just tell you that it's temperature dependent. So it's a form of energy that you need to know the temperature to be able to calculate, right? So so therefore it is a form of heat energy. And an example would be you take a lump of coal and you heat it up, right? And so the lump of coal experienced an increase in internal energy. And it's basically it's what it is, it's really microscopic energy. Energy, because what is this energy is associated with a temperature rise, right? A temperature rise, if you have basically this lump of coal and you heat it up, then the molecules inside, it's not as easy, inside of a gas chamber, it's a little easier to describe, but you basically have these atoms, right? And they have these bonds, right? And by you heating them up, the bonds start to vibrate. Right, so you got another atom here. The bond starts to oscillate back and forth, right? So there, you got these are basically bond vibrations. And so, really this thing is vibrating back and forth. The hotter the more energy you put into this in the forms of heat. So Q being heat energy. the bond's vibration is how we determine temperature. They are actually proportional to the temperature of so that's a proportional symbol there. Proportional to the temperature. So the more bonds vibrate, the higher the temperature. And that's how, so that is a form of energy. And we need to really know the temperature in order to calculate that. Now, the other forms of energy, so kinetic energy, we don't need a temperature. Right, so we know the kinetic energy is equal to, what is it, 1/2 mass times velocity squared. And the potential energy is equal to, what is it? It's equal to the mass times gravity times the height. Right? So it is a form of energies. Now, in our class, we like to do things in lowercase letters instead of uppercase. So assuming this was an uppercase K and an uppercase E, the lowercase usually means that it's kinetic energy divided by the mass. We like to make systems mass independent, and so therefore the equation becomes 1/2 v squared. And then the units would be something like a kilojoules per kilogram. The units here were just kilojoules. Right. And this is more kilojoules per kilogram. Same thing could be say about PE. It's equal to, you divide the mass out, so it's equal just to GZ, right? And the units are the same thing, kilojoules per kilogram. Okay. So the total energy, we say it's capital E, and it's something that's capital U plus capital KE, which is the kinetic energy, and this is the potential energy. Yeah, the capital UE is basically internal energy.
Professor?
Yes.
So just looking at what you said for potential energy on the equation, for that one said mgz. So is z the distance or the height?
Yes.
Right? Okay.
Yeah. So exactly, it's the height. I know sometimes height is is h.
Yeah.
H is used as height. Yeah.
Exactly.
And the reason we don't use h here, because the h will get you confused, is I mean h stands for height, but in our class it's a form of energy that's called enthalpy.
Okay.
That's why we don't use h and I use z. But like when we were talking about at the beginning, chapter 1, we were using h a little bit, right, liberally there, kind of putting it as height, thicknesses of liquids. So yeah, it's a little confusing, but yeah, the z is definitely the height. Okay.
Okay, and then with the KE right there, is that lowercase k e?
This one?
Or on the next part over where it says KE equals KE over M, I'm just wondering if that's supposed to be lowercase ke?
Yeah, that's exactly. This is lowercase and this should be uppercase. This is capital K, right? Capital, yeah, exactly.
So what makes the difference between the lowercase and the capitals?
The lowercase means that we divide by mass. So it's going to be like that in you'll see this throughout the class.
Okay.
When we use lowercase letters, again, this should be a lowercase p. I know it's kind of hard for me to draw with these pens. Lowercase usually means you divide by mass, right? So it's you divide, right? That's the general. Uppercase is obviously well, this is velocity, so there's no such thing as velocity divided by mass. But anyway, for volume, lowercase v would be volume divided by mass. So yeah, so this is the terminology.
Okay.
Okay, and then so lastly, this is internal energy. So therefore, little e. So speaking of that, little e would be a little u plus little ke plus little pe. And so the units of total energy are kilojoules. The units of specific, what we call specific energy, or energy divided by mass, is therefore kilojoules divided per kilogram Okay. So now let's see. We're not ready for an example yet. We're getting there. So I told you about what internal energy is. It's this bonds vibrating. So let's focus a little bit about mechanical energy. Mechanical energy. So we're going to say lowercase. This is a energy divided by mass is the lowercase e, and we're going to say E mech because it's mechanical energy. One thing I didn't mention is that there is another form of mechanical energy. It's called flow energy, and it's measured by pressure divided by density of a certain flow. And then there's the kinetic energy, and then there's the potential energy. All right, and we all know that the units are kilojoules per kilogram. Right. So now this is now per unit mass, right? So now there's we can introduce capital E mech, which is the total energy. It's not unit mass. That's not divided by mass. And then there's this dot. So what happens? The dot comes from now a flow rate, because now we have this first part here assumes flow, right? So if we had flow going into that room with the refrigerator, we can actually determine how much cooling is done by that flow, or how much energy is being taken away by that flow rate. So what we do now is we introduce an m dot, and then we say m dot times E mech, little e mech, right? Because this is a specific, so we have to get rid of the per kilogram, we have to multiply by mass. But now this is an m dot, so this is a flow rate, so it's a mass flow rate. So m dot, the units for m dot are kilograms per second, right? Those are the units for flow rate. So now we have m dot E mech, which is equal to m dot, and then of course it's what I just wrote up at the top there, density plus v squared divided by 2 plus gz. And therefore, yeah, so that's how we treat, this is now energy rate. So the units would be, since we're doing energy rate, so it's kilograms per second, so the kilograms comes out of the denominator here, and it's replaced by a seconds, and so the units are actually kilojoules per second, which is equal to a kilowatt. Right? So a joule per second is a watt. So now another way that in this class, typically we're only looking at changes. So we don't really want the total. We don't necessarily just care about the total potential energy of something or the total kinetic energy. We're looking for a change of kinetic, a change of potential, a change of pressure, that kind of thing. So we have a change of E mech. We're going to tell you how that looks like, is equal to, instead of P, we say P2 minus P1 divided by the density, assuming the density is constant, plus V2 squared minus V1 squared divided by 2, plus the gravity times Z2 minus Z1. And that gives us the height, right? The height, I mean, I guess you could have just left it as, this kind of captures the height change. Because you can have flow going from a certain height, you know, this way, and then dropping down to another height there, right? And so this could be like a Z1, and now this is Z2. And so the flow going down a pipe, coming back down, you know, there is a drop in potential energy, right? So that would be captured by this term here. All right, and therefore, to sum it all up, you can do the same thing at the total. The total change of energy is equal to m dot times what we just wrote at the top there, E mech. That gives you the rate. So this gives you, in terms of flow rate, as opposed to total, energy. This is now the flow rate. So now you're really getting into units of kilowatts. All right, let's do an example. So in
Yes,
your
sir.
book, it's 2-2. Yeah.
Just
ahead.
to clarify again with the dot. So when you have the dot mass or the dot energy, what does that mean again?
So the dot is so m dot is it's the mass flow rate. So just say mass rate. So it's a rate. So the dot is actually a rate, which means it's basically something per second, right?
Okay.
That's the rate. So mass rate would be a kilogram per second, right? Okay, that's what the dot's like. Every time you see a dot in this class, we're now doing rates, and your units go from, again, now you're not really doing kilojoules anymore. Now you're doing kilowatts.
Okay.
Right. Exactly.
Thank you.
Okay, you're welcome. So in your book, there's an example 2-2. If you have your book handy, or if you want to follow along later, go ahead, and we're just going to go do this. I don't think that, no, that problem was in the slide packet, so I'm not going to. So so the example, it has to do with wind energy. And so what you have is you have a wind turbine. And the wind turbine is basically standing on a, above the ground, but doesn't have necessarily, I mean, that's the assumption, right? Wind turbine out in the desert somewhere. And you have, so that what it's saying is, it's asking us, it's giving us that we are looking at a site that has the average speed of the wind is equal to 8.5 meters per second. And so we want to see how much energy that we can grab from that wind, right? And so what we want to do is assess if this is a good site to put a turbine. So what they're asking us to find they're saying find the energy. Sorry, I got to turn on my light here. Getting dark in here. It says find the energy per unit mass. Sorry. Let's see. Determine the wind energy per unit mass, A. B, for a mass of 10 kilograms, and C, for a flow rate. So we're going to find the energy per unit mass, right? B, find the energy, it says, sorry, for a mass. So we're going to find the total energy for a given mass. I would just say for a given, sorry, my screen just went dark. For a given mass. And C, find the energy flow rate. Okay, so the way we do that is we know that little e, since we're doing, this is actually little e. Maybe I can just write it up here. Little e is equal to, it's pretty simple. It's velocity squared, right, of the air divided by 2. And we know that it's 8.5 meters per second squared, and then we divide by 2. And so this is actually equal to 36.1. Now the units, if we did the units straightforward, right, because the units are meters per second, right? So the units are actually meters squared per second squared. So if you ask me if this is the right way of using units, I don't think so, because energy, I told you we want to measure in terms of joules. Or if it's an energy rate, it's going to be watts, so it's going to be still joules per second. So this is not the way I want you to place it, right? So then you would need to convert, right? And to convert, you can do, right? You can actually convert into fundamental units, but it's real easy right now. I'll just tell you right now. I'll do over here that 1 meter squared per second square is equal to 1 kilojoule or 1 joule per kilogram. Now it's not a kilojoule per kilogram, but it's not a kilojoule per kilogram. It's a joule per kilogram. So, and again, it's easy to determine that, right? Because if you break the joule into fundamental units, it's a Newton per meter, but what's a Newton? It's a kilogram meter per second squared, and that's times a meter, right? The Newton per meter divided by kilogram. And so it turns out that the kilograms cancel out, and you're left with meter squared per second squared, right? So it's a 1-to-1, and so you're it's as simple as just saying this is equal to 36.1 joules per kilogram, and be done with it. All right, but it's not always as simple. Sometimes you can get tripped up. Sometimes, again, this is a joule per kilogram. I guarantee you in chapter 5, we never use joules. We're always dealing with kilojoules because we start using tables in the back of our book and they're all in kilojoules. So if you assume that this is it's easy to kind of, when you're doing an energy analysis, is to assume that by accident that a meter squared per second squared is equal to a kilojoule per kilogram. And this is where you get killed, right? Because this is a kilojoule per kilogram. This would be 0.0361 kilojoules per kilogram. And you start realizing that's pretty small compared to, for example, if you did a thermal analysis and the enthalpy change was 800 kilojoules per kilogram, and then you add mistakenly add, assuming that this was a kilojoule per kilogram, you add 36.1, you're gonna get the wrong answer by a long shot. So be careful here, all right? This is it's always good just to put the unit conversions into your problem. Okay. All right, so that solves that. For B is easy because you have it's 36.1 joule per kilogram, and they give you have to multiply it by a given mass, and the given mass is 10 kilograms. This should be right. So therefore, the answer is 361. It's not joules per kilogram anymore; it's just joules. That's B. C, well, we're looking for E dot, right? And that's equal to M dot times little e, right? Which is equal to, what do they give us? M dot is 1,154 kilograms per second. And so this is a large fan, all right? In order for this fan to experience this much mass per second, this thing must be one of those huge turbines from the desert. And then you multiply by EMEC, which we found it for part A, 36.1, right? And this turns out to be 41.7 kilowatts, which is huge. 41.7 kilowatts is pretty good, right? You only need about 2 kilowatts to power a house, anywhere from 2 to 8. So 41.7 can power, right, 20 houses or so, 10 to 20 houses. Okay. Any questions on this? This is kind of how you would use what we just learned.
Professor?
Yeah.
So the lowercase e, what does that represent?
This is lowercase e is energy per mass, per unit mass. Yeah. Yep. And since we're multiplying by mass, right? So that's total energy, which is capital E. And because this mass is the mass rate or mass flow rate, which has a per second, then we put the dot, and therefore the kilograms time divided by seconds, and then this was joules per kilogram or joules per kilogram. So the units become joules per second or kilowatts. Okay. Any other questions before I move on? We got 10 minutes. All right. So actually, this is where I ended up my last class. I had a lot of people were asking me about homework and stuff like that. So right now, if you want, does anyone have any questions on the homework? Or is prepared to ask me something? Because I think we spent 10 minutes, and that's why we ended up here. So if there's no questions, I'm going to stick around for office hours. But does anyone have any questions in general? So, yeah, go ahead.
Professor, for question 3, how do we set it up exactly?
Okay.
on the
So,
homework.
all right. So question 3. Which one is question 3? Is it the blood, or is it the tank that has a different levels?
Tank.
All right.
Mm-hmm.
All right. So the tank. Let's see if I get lucky and have this. No, I don't have the prompt. Okay. So if I can go ahead and draw this, because that was the same question that was asked for me. So I have a tank, right? This is kind of almost like a milk jug. And then it has, so this is, I'm going to show you how to set up the problem here. It's a milk jug. It has, I think, 3 layers. Something like that. And each layer, I don't know what the stinking layers are. This, and then I know the bottom one was yellow. Oh, I had a break in my, sorry, break in my tank lining here. All right, so now I can do this. So yeah, so then there was yellow here, and I'm just gonna say blue there at the top. All right, and then you had definitely you had a pipe coming out. So something like this, right? And then you had another, like, okay, I'm gonna go back to my brush. All right, so you had basically a pipe going like this, like that, and then going all the way up, right? So I'll try to do a line. Then, all right, so then I'll do another line. All right, so this is the homework problem. And at the top, you have a pressure gauge. Right. So then there's fluid. So I don't know if this is going to fill. Again. So anyway, you have fluid filling up this tube here. So there. Okay, good. And then you have the pressure gauge right there. So I think the question is, how do you set it up, right? You need to find. I think it's asking you to find right here, PA. I think P. I'm just gonna say pressure. P. I'm gonna say P. They want you to find P of that gauge. Okay. Oh, anyway. So how do you set it up? So what you do is you're given all the heights, right? You're given the thicknesses here. You're given, I think that this is water, and then all the different fluids. So what you do is, we talked about this, right? So this is a tank that has an opening, right? So we know that out here is atmospheric pressure, right? So you have to. So what you really got to do is you have to use the method of the manometer that I went over the last time, and you got to start basically using all these heights and densities, right? So it's 1, density 2, and density 3, and then you you need to find P, right? So you have to go and you have to basically go strong arm it, basically look at every start from the pressure at atmosphere and go and end up all the way to P, right? So to do that is you start here at the very top. What's the pressure there? Well, the pressure there is P atmosphere, right? And then I go down. I imagine myself going down this tank and stopping at the next fluid to fluid interface, and that's this point there. And so what I did is I went down. I don't know if this is water at the beginning, but I went down this column of water. So therefore, I increase in temperature as I walk down, or as I swim down that column of water by rho g, and it's H1, right? So this is 1, and then I go to the next through the next liquid column, and that I increase in pressure again, rho 2 GH2, and then I go the same thing again. Go down here, increase again, rho 3 GH3. And then I cheat, right? I go across and I come out and I said this, the pressure here, the pressure at that point is the same as here. If I go horizontally, it turns out that they give us what this distance is here. I think it was like 20 or something. I don't know. I don't know if I want to write that down, but it might have been 20 centimeters or something like that. And I think up here is 90 centimeters, what I remember. Oh, it's 15? Okay. Sorry. Sorry, it's easier if I just write 15, if I erase everything. And then it's 90 here or 70? Do you remember?
90.
90. All right, 90. Right. All right, so so therefore I know that the pressure here is the same as the pressure there. So now I need to say, well, I have a straight fluid path all the way to the pressure device. And I say, well, so I go from this point to P, capital P. I'm actually rising up the column of fluid there. So I'm going to say it's minus. So I'm going to experience a pressure drop, rho 3 G. And now for H, it's this H here, which I'll just call for now. It's 90, right? But I'm just going to say it's equal to H4. So H4. And then I end up at my final destination, and then I put an equal sign there, and I say that what's the pressure there at that P? Well, it's P. It's what I'm looking for. So now I know everything here, and I just solve for P. Everything has been given to me. So in reality, since these two terms here these are like terms, right? Because they have the same density. So it basically becomes this plus that plus density of the third fluid G times it's the height difference between, or it's basically the height change from here to here. Basically, that's so. But basically, this is what you're going to solve, right? This is the problem. The problem you're solving here. Why is it? Yeah. All right. Sound good?
Thank you. Yeah. So you're
Okay.
only subtracting the last fluid, right? You're not subtracting like more than that.
Right. I mean, you're looking at, so this 15 centimeters is useless information, and it's probably only meant to, it could be 1,000. It doesn't matter how much it is, because it could be 1,000 centimeters, right? All you care about is when you're in this yellow fluid, right? So there is a fluid path that goes from here to here to here. Because what happens is, yeah, you increase pressure here, but then you decrease the same amount as you go up. So this U cancels itself out. So that's why I'm saying you could always assume if you're within the same fluid, even if it's a U tube, then as long as you're horizontal, that pressure there, all of the horizontal pressures are the same, right? Everything here, everything there, and everything there are the same. So therefore, I disregarded the 15 centimeters. I didn't need it.
Okay.
And then the manometer problem, they didn't even give us what this was, right? But here they're kind of trying to throw you off, so you don't need it. So it turns out it's basically just that last part is basically the difference between H3 and H4. It's actually between it's this like this. You could have gotten fancy, but anyway, I just want you to use that manometer approach to solve these problems. That's all, and then you'll be all right.
Thank you.
All right, you're welcome. Any other questions? We got 1 minute.
Professor?
Okay. Yeah.
Why do you use PATM if you're trying to solve for gauge pressure?
Oh, is this gauge pressure?
I think so. That's what I read.
If it's gauge pressure, then you don't need PATM, because, well, what happened is if you say, well, if P gauge is equal to P absolute. So we found P absolute. This is P absolute, everyone, because it includes atmosphere. So then it's just minus P atmosphere. So in a sense, if you needed to give me P gauge, you have to subtract the atmosphere out. So this would if this was P gauge, right? If we're going to solve P gauge, then just P atmosphere, just rip it out, because you got to, you have to subtract it off anyway. Because remember, P absolute is equal to P gauge plus P atmosphere, right? That's the
Yeah, I don't even think the P atmosphere was even given in the problem, so
no.
that would even
Okay.
clear up another confusion.
Okay. Yeah. Well, sorry. But yeah, that's because I looked at it because someone shared the problem with me. Honestly, I don't remember this problem. Someone shared it, and I thought that looked like a tank with an open atmosphere like that, and so you know. Anyway, if you gave it to me like this, I wouldn't mark it off. You know, I'd be, because then if you included atmosphere, you're giving me P absolute. If you said, right, so anyway, I wouldn't mark it off wrong. Any other questions? I think we're done. So if anyone has any questions, stick around. Ask me. I have office hours till 8:30, and everyone else, if you guys want to drop off. So look at this site here again. At Teams here. Later today, in this chat bar, MAE330-11. It's basically it's gonna be a little blue circle with a calendar in it, like that, a meeting calendar. It should be the recording should end up there. All right, for this lecture. If you guys want to come back and check out the lecture, it said, watch when I do that. If I stop, I'm going to stop the recording now. Stop recording. It says this meeting is being recorded. Are you sure you want to stop? I say stop recording.